Ladies and gentlemen, welcome back. We are still in section 5.4. This is the so-called other types of discrete probability distributions. This is video number 4 of section 5-4. All right, so now we're going to talk about the hypergeometric distribution. Now, the hypergeometric distribution shares some similarities with the binomial distribution. I've mentioned this before. Let's just think about this for 1 second here. The binomial distribution deals with two possible outcomes. One of the requirements is that each of the trials has to be a independent event. If you look back in the textbook, the various requirements for a binomial, it has to be independent. And so one of the ways that we manifest this, or one of the ways that independence or lack of independence can be considered is, do we have replacement or do we not have replacement when we're sampling? So in a perfect world, a binomial distribution would have replacement, because if you don't have replacement, that changes the probability. Classic example is drawing a card from a deck of cards. If you draw a card and you want to know whether it's red or black, and you put it back in, you are replacing the card. So that satisfies the requirement that each trial is independent. You are sampling with replacement. All right, suppose you're not sampling with replacement. Can we never use a binomial distribution? Well, the answer is we can use a binomial distribution if the sample size is small compared to the entire population. So you may recall a problem we had where we were dealing with selecting 10 human beings out of the population of the United States, and we said at that time the sample size of 10 is so small compared to the entire United States that it really doesn't matter whether we are replacing or not replacing. Every time I take a person out, I don't replace them into the population, but it's close enough for government work. We can use the binomial distribution. Okay, so that's what we did before. Now we're going to talk about a situation where, for whatever reason, we don't want to play that card, so to speak. We don't want to play that game. We don't want to say, hey, the sample size is small enough to where it's close enough. What we want to do now is we want to say, hey, listen, I don't care whether there's replacement. We can use this distribution. So here's the distribution. It's called the hypergeometric distribution. So he says right there, when sampling is done without replacement, the binomial distribution does not give exact probabilities since the trials are not independent. And then the smaller the size of the population, the less accurate the binomial probabilities will be. I'm not sure that's true. Let me think about that. Okay, my bad. It said, this just goes, I'm not correcting this tape because I want you to see that, no matter how many times I teach this class, I still learn new things. It says the smaller the size of the population, the less accurate the binomial probabilities will be. When I saw that I read population, but my mind said sample, and so that's what was throwing me off. I agree with this statement. The smaller the size of the population, if you have a small population, you're not going to have a sample size that is small with respect to the population. So if the population is the entire United States, that's a huge population. You can take a sample out of there and it doesn't matter whether you replace or not. If you have, on the other hand, the population is, like 100 kids in the senior class, well, now the population is so small, if you don't replace, you're not going to get a very good probability. So it's the size of the population. If the size of the population is large, you can play this game with a binomial distribution. Okay. Now let's take an example here of what's going on with the hypergeometric distribution. And the way the author chose to do it this time is he said, let's just take an example here. Let's work our way through an example, and we're going to figure this out. We're not going to use the binomial distribution. We're going to solve this problem just by using the basic rules of probability. So here's the scenario. Suppose a committee of 4 people is to be selected from 7 women and 5 men. Okay, sounds reasonable, right? You have 7 women, you have 5 men, so there's a total of 12 people. And you're going to pick a committee of 4 people from those 12. Now, when you pick somebody, you don't put them back, right? You don't take John Doe and then you put them back. So every time you select somebody, you're doing it without replacement. Therefore, it's not independent. All right, so the question is, the call of the question is, what is the probability that the committee will consist of 3 women and 1 man? So that exact result is what you're looking for. Okay, how would you solve this? To solve this problem, you must find the number of ways a committee of 3 women and 1 man can be selected from 7 women and 5 men. So doesn't that sound familiar? Isn't that what we have been doing in the past? We would select, we would have, in this case, we would have 7 women and we choose 3 of them. So 7 choose 3, and it's a committee, and we're not assigning any particular role. We're not saying someone's a president, someone's a vice president. We're just putting them in a box, so to speak. So the order doesn't count. There's no arrangement. So it's 7 choose 3, and it's a combination. It's not a permutation. It's a combination because we don't care about the order. So to get 3 women out of the 7 women, how many ways can we do that? It's 7 choose 3 combination. We have a formula for that. To get 1 man out of the 5 men, that's 5 choose 1. And again, it's a combination, and we have a formula for that. So here's what it works out to be. Multiply it out. Boom, you have 175. So there's 175 ways of choosing 3 women out of the 7 times, and then you multiply that times 1 man out of the 5. So basically what you're doing here is you're choosing the women, then you're choosing the men. They're independent events when you choose them, because when you choose the women, you're not choosing a man. They're disjoint sets, right? So when you choose the first woman, that doesn't affect anything in the men's category. When you choose the second woman, that doesn't affect anything in the man's category. So choosing the women is independent from choosing the men. So we're good in that respect. So we can multiply. This is one of those rules of probability. You just multiply the probabilities if they're independent events. So in the numerator, there's 175 ways of choosing this situation, or this scenario, the 3 women and the 1 man. 175 ways of doing that. Okay, that's for the numerator. That's the number of successes, 175 ways of doing this. In the denominator, as always, in the denominator, it's the number of occurrences in the sample space. So again, using our old friend combinations formula, the total number of ways that you can pick a committee of 4 people can be selected from 12 people. That's 12 choose 4. That's 495. Okay? All right. So now we have the top and we have the bottom of the probability fraction. So the probability of getting a committee of exactly 3 women and exactly 1 man from 7 women and 5 men is, the numerator is the number of successes, the denominator is the number of occurrences that's in the sample space. It all works out to be 35 over 99. So that's the probability. Well, that's a little bit tedious, right? Okay. And even if it were not tedious, math guys, they always just want new ways of doing things. So there's a way of doing this that's more generalized, and that's what he's saying right here. The results of the problem can be generalized by using a special probability distribution called the hypergeometric distribution. Now, you know, I like to take apart the sentences. I don't know what the word special adds to this sentence. I guess all probability distributions are special in some sense. So I don't really think the word special adds anything here. Okay, it's called the hypergeometric distribution. Okay, here's the definition, the brief definition. It's a distribution of a variable, has 2 outcomes, and the sampling is done without replacement. See, if you were doing it with replacement, you wouldn't need this. You would just call that a binomial distribution. But we're doing it without replacement. Therefore, we're going to use the hypergeometric distribution. So here's the formal definition. All of these are pretty straightforward, right? Fixed number of trials, 2 possible outcomes. We're going to call it a success or a failure. And the sample is selected without replacements. Well, this next formula here will make you crazy, all right? It's a very odd formula, looks very, very difficult. In any event, the probabilities that we're looking for can be calculated by using this formula. So first of all, let's make sure we got, what is the left-hand side? This is the left-hand side of the equation. This is the right-hand side of the equation, okay? X is X is the number, you're counting now, X is the number of successes. How many successes do you have? Do you have 3 successes? Do you have 4 successes? How many successes do you have? Okay, give me 1 second. Okay, so X is the number of successes. Unfortunately, in my view, the author changes his notation here a little bit, and I'm sorry he did that, but we'll work our way through it here. So we're given a population. There's only 2 types of objects: females and males, defective and non-defective, successes and failures, right-handed, left-handed, boys and girls, Republicans and not Republicans, you know, all kinds of things that you could put in there. Okay, but there's 2 of them. There's 2 types of things that we're dealing with. Okay, well, there's A. See, A is like a variable, so to speak. This is the number. There's A, like say there's 12 items of one kind and B items of another kind. So maybe there's 12 of the first type and there's 13 of the other type. A plus B, the 12 plus the 13, is the total population. Now, so far that makes sense, I hope. The notation's a little weird, but I hope at least that part makes sense. The first category, there's A of them, say it's 12 of them. The second category, there's B of them, let's say there's 13 of them. So add up the 2 categories, A plus B, that's 12 plus 13, that gives you the grand total, okay? So now we say, well, the probability, P of X, of selecting, and again, we're doing it without replacement, a sample of size n. So now this is what I don't like. He's using size n in a different way. He's using n as the size of the sample from this population. So that's kind of what we've been doing in the past, and we're certainly going to do it in the future, but I just feel like it's a little bit different from what we've been talking about before. But we're all grown-ups, we can handle this. So we're picking a sample of size n, and we're going to say, well, there's how many of type A do we have? We have X of type A. So there's X successes, and if there's X successes, there's got to be n minus X items of type B. That's just, you know, that makes sense, right? Okay. Well, the probability of getting that, of getting X successes, is given by this formula here, which looks horrible. But I suggest to you that in a minute we're going to do an example, and it's not as bad as it looks, okay? Okay, so now let's just think about this one more time here. So we're picking a size, the sample size is n. We have X of type A and n minus X of type B. Do you see where that comes from? Let's say there's 25 altogether, and we pick X items of type A. So if we have X, let's say X is 3, okay, how many do we have of the other type? Well, we have 25 take away 3. We have n take away X items of type B. So it's a little bit, I don't like the notation here, okay? He's using A items of one kind and B items of another kind. Those are numbers. And then here he's talking about, well, it's type A and type B. So he's kind of mixing up these letters. On the one hand, they're an actual number, and on the other hand, they're an actual type. So it's a little bit confusing there. But I think if we just work our way through the formula, or I'm sorry, if we work our way through the example, I think we'll be okay. So let's take a look at this first example here. We'll do that on the next tape because I'm running out of time. So this is the end of the first tape. The next video we're going to do example 531.